Okay, so we've gotten to the point, we've done long division, we've done synthetic division, and we've already factored quadratics. So this is kind of the end-all be-all video, which allows us to factor cubics with a new method using what's called the rational root test. So if you haven't looked at the synthetic division video or the factoring quadratics video, I would go ahead and look at that now. And we're going to just try and dive in and factor some cubics. So first, this cubic is almost disguised as one. It is, but there is something in common between all of them. All the terms have an x. So when we divide x, we get this, and that cubic, we technically factored it because it had something in common from the start. So that can happen. Or you can get something like this, where we do factor by grouping, where you see that both of these first two have an x squared, and you divide that and get this, and both of these have a 3, so I can take that out. And at the end of the day, both of these clumps of terms have an x minus 5, so I can take that out, and you're left with just this. So this factor by grouping only works with cubics that have a quadratic, but it doesn't have a middle term. It's like 2x plus 0, or I'm sorry, it's x squared plus 0x plus 3. Okay, only when you do enough of these, you begin to notice that factor by grouping only helps when the quadratic that's going to be factored looks like this. So it doesn't happen all the time, basically. If you had something like this, yeah, these have an x squared in common, and these have a 4 in common, but when you take those things out, you're kind of left with garbage because nothing's in common anymore. So even though we got halfway through factor by grouping, it doesn't work. So there's got to be a way to check to see if you can factor these type of cubics. And we do have a way. And the way is called, basically it's division, right? If we know what to divide by, we can factor this. So like, for example, if we knew that, I believe, x equals -2 is what's called a 0 or a root to this. Basically, if we take -2 and we do synthetic division, which I encourage you to watch that video, and if we bring this down, multiply, add down, multiply, add down, multiply, add down, we get that marvelous 0, which means it can be factored. How? It can be factored the original cubic equals what we divided by. Remember, from synthetic division, this is really x plus 2. And we got an answer, this, which are the coefficients of the polynomial. So it's x squared plus 4x minus 4. Okay? So there is a way to do it. But the question is, I told you this. I told you that we can synthetically divide with -2. I told you that. But what if you were completely on your own, and all you could do was just, I guess, aimlessly try to divide stuff? Right? That's not good. There's got to be a way we can narrow it down, and that's what the rational root test can do for us. Now, it doesn't always work, but it can do us some good to help factor these long polynomials. So here's a statement of what the theorem says. So first of all, when I say rational, think fractional, or think as a fraction. Okay? Pretty much the same word, right? The rational root theorem gives you a list of possible roots, or really factors. For us, we're factoring. And we're not going to go into exactly what a root is. I mean, it's an x-intercept. And like, for example, if we look at a cubic like this, and we say, oh, this intersection's at 0, this intersection's at 2, this intersection's at 4. What you can do is you can write the cubic as a product of these factors that we've been dealing with, and this is the equation, or a close equation to the cubic. There's a number out here that we need to watch out for. But basically, when it's in fully factored form, you can see the roots of the cubic or the quartic or the quintic function. And these are the things that we divide by when we long divide. Or when we synthetically divide, right? We try and divide by these numbers. And by dividing by those numbers, because they are a factor of it, it can simplify the cubic. And that's what we're doing here. So it's basically telling us if this was our cubic, what you can do is look at all the factors of 3, which are 1 and 3, and all the factors of 6, which are 1, 2, 3, and 6. And if you look at, as a fraction, any factor of the constant over any factor of the leading coefficient, and that ends up being a candidate for maybe being one of these roots on the function. So let me show you what I mean. So this is the constant, and this is right here, this 1 right here is the leading coefficient. Coefficient is a fancy word. It just means the number in front of the variable term. So the possible roots for this is you just do all of the roots of the constant, which in this case is just 1, over all of the roots of the leading coefficient, which is also just 1. So the possible roots are either +1 or -1. And if those don't work, sorry about your luck. Maybe you can't factor this cubic. Okay? Maybe it has roots that are irrational, which happens all the time. But we're looking for good roots that can show up in factors. So we're looking for fractional roots. And in this case, it's 1 and -1. So what I want you to notice out of all this is what can you do with that information? Now that we know that those are possible roots or possible factors, how do we know which one works? You set up as many synthetic divisions as you need. So I'm going to try synthetically dividing by 1 and also by -1, and we're going to see if we get lucky and get a remainder of 0. So if I bring down this 1, I'm going to multiply by 1, bring down, multiply by 1, add down, multiply by 1, add down. This 10, no good. That means that x minus 1, which is the same thing as the 1 here, it is not a factor of our cubic, and x equals 1 is not a root. It's not an x-intercept. It doesn't show up when we expand out the cubic. So that's no good. We failed there. But let's see if this one works any better. So if we bring down the 1, multiply by -1, add down, multiply by -1, add down, multiply by -1, and there you go. You got a 0. That means, if you remember from synthetic, if this is x plus 1, then the cubic, this guy, up top, did I write it down here? Oh, guess not, is equal to that factor that we just used and this. So 1x squared plus 3x plus 1. By knowing the possible roots and by testing with synthetic division, we were able to factor the cubic. And does this work all the time? No. Sometimes all your possible roots, you tried, but none of them work. The cubic's just kind of a not so nice one. And that happens most of the time. But sometimes you can find a root this way, and it's really rewarding when the synthetic division works. So let's try out a couple more. So this one, the possible roots are, we're going to take this number, fully factor it out here, and we're going to take this number and fully write down every single number that can divide 2. So the only factors of 2 are the 1 and 2. And I picked these easier ones to start with, right? So 1 and 2, right? And we do have a plus or minus here. And then the factors of 2 again are 1 and 2. So we can take, there's really 4 things that could happen. You could take the 1 and divide it by the 1, or you could take the 1 and divide it by the 2. So this divided by this, or this divided by this. Or you could do 2 divided by 1 and 2 divided by 2. But 2 divided by 2, we already had that on our list, so I'm going to erase that. So the answer, or all the different possible roots you can get, are plus or minus 1, plus or minus 2, and plus or minus 1/2. These are the 3 possible roots, and then it can be negative. So we have a lot of work to do, don't we? Because we have to test 6 different things with synthetic. And that's a lot of work, right? So let's see. I'm going to duplicate this. Hopefully we can get it in 3 tries, but let's see. So I want to take these numbers over here. I'm just going to pull one of them. How about let's try 1. 1's easy to do. So I'm going to bring down the 2, multiply by 1, bring it down, multiply by 1, bring it down, multiply by 1. Hold up, look at this. We got 0 on our first try. I was expecting to have to try 2 and -2 and even maybe a half, but we didn't need to. So this is the golden key right here, and we can write our answer. So the I thought I wrote summaries down here, I guess not. So the cubic up top with synthetic division, and this was using the term x minus 1. And we found that it ends up with 2x squared minus 3x minus 2. Right? Definitely got lucky here. Without a hint, or without me kind of picking the ones strategically behind your back, this can be a lot of work to test all 6, which is why when we do these problems, we like to look also at graphs. And when we look at the graph of this cubic, which is the red curve, we're really looking at these 3 points, and we're seeing if anything looks kind of good. Like, for example, this one. It says 5, 0. That's a hint, okay? So let's keep that in our back pocket. That 5 actually might be the golden ticket here. So rational root theorem says that you take all the factors of 15, 1, 3, 5, and 15, and all the factors of 1, and you mash them all up. So plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Those 8 are your only rational choices, or choices that can be written as a fraction. Basically nice ones. They're really it's just a nice root test. And yeah, so we would test all these. So for example, if I were just going at this, I might guess, ignoring our little hint in our picture, I'm going to say, let me try -3. That's right here. It's one of our 8 choices. So I could bring this down, add down, multiply, add down, -11. Feels a little awkward, right? And then multiply by -3, 33. Oh man, this isn't looking good. Nope. But if I try 5, bring down the 1, multiply by 5, add down, right? Multiply times 5, add down, multiply times 5, add down, we get the magic 0. And it's this picture that tells us how our cubic factors. So our original cubic that a little smaller, is equal to what? Remember, when you put a number here, it's x minus that number. That's the factor. So we synthetically divided by this, which of course, check out that video if you haven't already. It'll help make all this make more sense. And then we also have this. So we divided by x minus 5, long divided, and then we got our answer is, these are the numbers, the coefficients of your answer. So it'd be 1x squared plus 4x minus 3. So, and we haven't talked a lot about graphs, but you can easily apply this to learning about graphs, that because we were able to factor this nice x minus 5 out of the cubic, that's why the graph hits nicely at 5 there. Okay? So that's just a taste of what the irrational root theorem says. It's like a way of creating a pool of possibilities for potential factors, nice factors, whole numbers or maybe some fractions that you can use to help you factor cubics. It's a really viable technique, and it doesn't always work. This one worked out, but we could easily have a cubic that crosses here and it crosses here at like the square root of 11 or something like that. And it's just not in the cards, but there is a lot of times a number that we can find and synthetically divide it out to factor a cubic, and it's a really sophisticated technique, but